right, so for this particular video, we're going to go over polar versus non-polar molecules. This is really important to understand as polarity of molecules determines a lot of their characteristics. So this is all dealing again with covalent molecules. Ionic compounds are already sort of their own thing. They're definitely polar, but it's a little more complicated than that. But we don't need to go into too much today. Okay, so the difference between a polar molecule and a non-polar molecule is the distribution of electrons. So a polar molecule has one part of the molecule that's very negative and one that's positive, because one part of it has a lot of electrons hanging out around it and the other part is has fewer. So it's an uneven distribution of electrons. There's a couple of things that can cause it. It can be what it's made of, the atomic composition, and it can also be the geometry if it's asymmetrical. So that's kind of the general idea. Non-polar molecules, all of the electrons are shared very evenly. So that might again be because of the geometry or what it's made up of. So there's a few, I can't give you any like specific rules, but there's some general guidelines and you can use those to figure out if a molecule is polar or non-polar. There's a whole other concept of electronegativity, but we're not going to get into that. That's more of an AP topic. So let's just dive right in. So let me show you some examples of polar molecules. If you have any molecule that they're asymmetrical, those are probably polar. So for example, HCl, hydrochloric acid or hydrogen chloride, and hydrogen fluoride or hydrogen monofluoride or hydrofluoric acid. These are both polar molecules. And the reason that they're polar is that they aren't really symmetrical. So there's two different elements. And one of those elements is going to have a higher electron affinity. It's going to attract the electrons more than the others. Going back to our periodic trends, we know that chlorine is going to have a higher electronegativity than hydrogen. That's the trend. We also know that fluorine has a higher electron affinity than hydrogen, and also definitely more than chlorine. So if we were to think about this conceptually, this end of the molecule, the electrons spend more time here because they're drawn to this half more often. So we say that this side has a slightly negative charge. We use this little Greek letter lambda to mean like a little bit. It means it's not really charge, but there's a little bit higher electron density on that half. And it's less on the hydrogen side, right? So if we kind of drew the electrons like a cloud, they're going to be ballooned over here, but not as much over here. And this side is going to be slightly positive. So it's again this idea of electron affinity, which element will draw the electrons to it more. The same thing is true for hydrogen fluoride. The electrons are just going to spend a lot more time near the fluoride side and less time near the hydrogen. Now, in terms of electronegativity, one question that you might get asked is not only is this polar or non-polar, but which one is more polar? In this case, hydrogen fluoride is definitely more polar than hydrogen chloride, and that's because the fluorine is has more electron affinity than the chlorine, so it's going to be able to pull those electrons away from the hydrogen even more than chlorine can. Okay, so water also is non-polar. Now, you might think, sometimes you draw water and maybe you would be tempted to draw it this way. And in this case, that might be confusing because this looks pretty symmetrical. But in reality, that is not true. Water is a bent shape. So in 3 dimensions, this oxygen is going to attract a lot of the electrons way more often than the hydrogen. So all the electron density is going to be over here. So this part of water is a little bit negative, And this side of water is a little bit positive because it's drawing away those electrons. Okay. Same thing is true for a tetrahedron. Actually, let me make a model real quick for that. We need a model. 1 second. Okay. So just to show you what that might look like, if this represents a water, so we've got the oxygen in the middle and the hydrogens on either end, and these are those lone pair of electrons. This bent shape means that the electrons are going to spend more time here and less time here. So this molecule will be charged. Not charged, but polar. It'll have a slightly positive and slightly negative side. Okay. This can represent this strange molecule. It's a carbon in the middle. It's got 2 hydrogens. And we'll just say this represents a chlorine and this represents an iodine. So what's going to happen here, the chlorine and the iodine are more electronegative than hydrogen. We could kind of tell that again by our periodic trends. So they're going to attract more electrons than the hydrogens. The chlorine is going to attract it a little bit more than the iodine. So most of the electrons are going to be definitely on this half, this kind of top or whatever side half of the molecule. And they're even going to be attracted to this blue chlorine just a little bit more. So again, not symmetrical. So I'm using this red to draw like kind of like an electron cloud, spending a lot of time over here and not a lot of time over here. So this side is a little bit negative and this side is definitely a little bit positive. Okay. So again, there's a couple of factors. It really depends on what particular elements are here and which ones aren't. Generally speaking, carbon and hydrogen together have pretty much the same electron affinities. So they're not really polar. But again, it just depends on the situation. Once you throw in an oxygen or a fluorine or a chlorine or even a nitrogen, things start looking a little bit more polar. Okay, let's look at some nonpolar ones. So nonpolar means all the electrons are kind of shared evenly. So hydrogen, if they're both the exact same element, that's very symmetrical. So all the electrons are going to be shared very evenly. So there's no differences in charge. So it's nonpolar. Same thing is true for oxygen. It's just 2 molecules, very even distribution of electrons. Same thing is also true for carbon tetrahydride, right? All of the hydrogens are the same electron affinity. So they're going to draw the electrons away from the carbon, or the carbon's going to draw the electrons towards itself. But either way, it's very symmetrical. There's not really one side that's different than the others, which was the case for this one, right? So this really had 2 different sides. It was it wasn't symmetrical. And this one's very symmetrical. So symmetricality is usually the key. It's really hard to know without the geometry. If you don't really think about what the geometry is, it's really tough to know, for example, that water is polar. You wouldn't necessarily guess it. Carbon dioxide is actually the same. So carbon dioxide, this is a double bond, is linear, right? So the oxygens are they have a high electron affinity. They're drawing a lot of electrons. So in actuality, the carbon doesn't have a lot of electrons around it, but the oxygens do. But because the molecule is so symmetrical, there really isn't one place. There's not one side or the other in any dimension. These 2 sides are about the same. These 2, it's all too symmetrical. So even that is also nonpolar. So when it comes to actually figuring these out, this is really important because nonpolar substances mix together and polar substances really mix together well, and then polar and nonpolar don't mix very well together. So for example, that's why I really like it, because I like to wear nail polish. Nail polish is a nonpolar molecule, and it doesn't come off when I wash my hands in water because water is polar and they don't mix together. But my nail polish will come off in acetone because acetone is polar. So there's this kind of general idea of polar and nonpolar things mixing together. All right, let's take a look, put those away, at the packet. So hopefully, there is a POGL that you might find helpful. It kind of goes through some of these ideas. It does talk about polar and nonpolar bonds, which may or may not be helpful to you. But yeah, it can kind of walk you through this. So if you're still struggling a little bit, this one might be very helpful. Okay, so page 12, you hopefully already filled this out. This is the shapes of molecules, the VSEPR geometry. These exact same molecules are the same ones for this page. So let's go over a couple of these. We'll draw some diagrams and let's determine if we think these are polar or nonpolar. Let's pick out something we haven't done yet. Oh yeah, NH3, perfect. So the shape of NH3 is trigonal bipyramidal, or trigonal pyramidal, sorry. So the question is, do we think that this is polar or nonpolar? This is definitely polar. And it's polar because this nitrogen here is going to attract a bunch of electrons because, again, it has two obvious sides to it. Yeah. In terms of, it would look something like this in terms of a model. This top part would be positive, this bottom part, or this top part would be negative, and the top bottom would be positive. And we know that because they're two different elements, and nitrogen is has higher electron affinity. So positive or negative, sorry, and this end is positive. Okay, how about, I'm gonna pick another one. How about I2? That seems great. This one is nonpolar. There's no one side, they're pretty much, it's very symmetrical. It's not really a lot of options there. Let's do HCN. I like HCN. Excuse me. Okay. So there is the Lewis model. So is this one polar or nonpolar? This one's definitely polar. Okay. The nitrogen is more electronegative, or sorry, has a higher electron affinity. It's the same thing. So this side of the molecule will be negative, this side will be positive. It's not symmetrical. It's a line, a straight line, but they're not all made up of the exact same thing. Okay. Awesome. All right, let's try the next page. Number 14, and then there's also 15. And I'm going to say, I'm going to make 15. I'm going to say 15 is probably optional. So you might not have to do that one, but it'd be good to try 14. Okay, so for each of these, we need to figure out which one of these is more polar. So carbon disulfide, or sulfur difluoride. These are weird. Sulfur. Oh yeah, it's not too bad. Okay. This isn't that hard. Okay, so it's good to draw out the molecules. So which one of these do we think is probably going to be more polar? Well, just looking at this is like just straight up non-polar. So the answer is definitely going to be sulfur difluoride. Because carbon disulfide, because CS2 is nonpolar, and sulfur difluoride is bent. So the shape really is what determines this. Also, it has fluorine. So because it's not, this is because it's linear. So linear versus bent makes all that difference. Okay. Let's do, what's a fun one? Silicon dioxide. Let's do number 5. I think this one's kind of fun. So silicon dioxide. I don't expect you to be able to draw these Lewis models this quickly. It might take you a minute. If you're not sure how to do these, please let me know and we can talk about that. but it's helpful. So silicon dioxide or carbon dioxide. Well, these ones are both linear. So the shape is the same. They both have oxygens. The only difference is the silicon or the carbon. So in this case, whichever one is going to have the higher electron affinity between carbon and silicon is at least going to make the possibility of it being slightly more polar possible. So it's going to be carbon dioxide because carbon is more has more electron affinity. So when you get a tiebreaker like this, you have to go with that. Yeah. Let's do number 6 real quick because methane is CH4. So we need to know what that is. Well, maybe let me see if there's a more fun one that we can do. CH4, so you'll need to know that. You know what, let's do number 8. So nitrogen trifluoride versus phosphorus trifluoride. You know what, I'm going to draw it and maybe we'll do it in class or you all can kind of try to figure it out. I just want to draw it this way because it's a little easier sometimes. Maybe you guys can tell me which one of these you think is more electronegative. Okay. Last thing. So yeah, definitely do page 14. You can also check out page 15. That's also very similar kind of idea. It's just kind of repetitive and maybe a little bit trickier, but not by much. Those you should definitely check out. All the other packet pages are at this point optional. This is intermolecular forces, which is very cool stuff. Very, very important for AP chemistry. It's a huge part of the AP chemistry curriculum. I'm going to make a video about it and I will kind of go through some of these with you. But if you don't think you're going to get around to it, if you run out of time, that's okay. We can cover that more later if we feel like it. Last thing I'll show you is I want to hop to my YouTube page because I pulled up some videos that might be very cool to watch. They're quite fun. Here's one on nonpolar versus polar molecules, so very cool. This one's cool. Why doesn't anything stick to Teflon? It has to do with polarity. The science of snowflakes, how polarity makes water behave strangely, why oil and water don't mix, the science of macaroni salad, and why does ice float in water are all related to these concepts. Especially anything with water, everything water does is because of this polarity of the molecule. It's really, really important. All right, I'm going to stop there and we'll continue on with the last little bits of notes. Thanks, y'all.